Hello, this is Greg Risteman from Olympus. I'd like to welcome everyone today to this webinar titled Toth Inspection, Time of Flight Diffraction, using OmniScan SX and MX2, and this is the Getting Started. This webinar provides an overview of basic Toth hardware and software setup using the Olympus OmniScan SX or MX2 flaw detectors. Our presenter today is Chris Magruder. Chris is a global product support specialist for Olympus phased array products. This informational webinar will last approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. We do not use the chat panel for Q&A. If we're not able to get to your question during this live event, they will be addressed personally either by email or phone after the event is over. Now, without further ado, I'd like to turn the presentation over to Chris. Chris, take it away.
Hello, everybody. Thanks for joining us today. We have another big turnout, looks like, from attendees all over the world at different times of the morning, night, and afternoon. Today's webinar is going to take us through the getting started portion of setting up a basic Toth group in the SX or MX2. We're going to do a brief overview of the Toth technology. In more detail will be included in the download, and then we're going to go through the step-by-step process for setup, acquisition, and analysis. Toth is a conventional UT technique that really hasn't changed for decades. It's very simple in its acquisition and setup, and all the expertise is weighted heavily on analysis and the inspection strategy to include the probe choice and zone configuration. Given the right probe, procedure, and equipment, the ability to set up a Toth group is fairly simple and can be learned in a few days, but analysis and sizing of flaws is very dependent on experience in the particular inspection. A basic Toth group is a single A-scan, unrectified RF waveform, typical of any conventional UT flaw detector. The raw A-scan for any flaw detector with pitch-catch capability can be generated similarly. It is the software in the B-scan imaging, the encoder capability, algorithms, and tools that allow the Toth B-scan to record data and be useful. But again, it's a single conventional A-scan, and it really hasn't changed in a long time. The Toth inspection is very dependent on the probe frequency, size, impedance matching, the dampening, all of those factors play into the noise of a Toth group. They differ mainly from a shear wave angle beam probe in that the Toth probes are highly dampened for a sensitive L wave inspection. The most common frequencies are 5 to 15 megahertz. Lower frequencies are used for thicker components. Toth probes typically have a very small diameter as compared to their shear wave conventional equivalents to generate beam spread and greater coverage. The most common versions of those are 3 to 6 millimeter probes at 60 or 70 degrees for a single Toth zone. And we can see that in the Olympus Toth probes and wedges, they go from 2.25 megahertz to 15 megahertz in different sizes based on the sound path. Toth wedges, like the ones pictured here, can be Rexolite with a short range approach, stainless steel that has some advantages for wear and durability and a little smaller exit point, and built in with the lines for the exit point and adaptions for water couplant supply and connection to mechanical scanners. And again, more so than conventional shear wave or phased array shear wave, the Toth inspection is very dependent on the quality and having the right probe and strategy. The ASME codes mandatory appendix, EN codes, excuse me, all contain general recommendations for both the number of Toth zones the frequency of the probe, and the angle and element size. These provide some rough guidance for the best case scenario and at what thickness a second or third top zone is recommended. As we can see, on smaller thin wall material, the angle is 60 or 70 degrees. The element size is very small. And as the sound path gets longer or the thickness greater, the frequency is reduced and the size of the elements are larger. The mechanics required for Toth inspection range from a very simple one-line encoded scan or full mechanized scanners for high production, adaptable to different components. They support multiple groups of a phased array and supplemented by Toth, support for remote pulsar receivers, ability to scan parallel and non-parallel as well. So the scanners, the mechanics, the encoders come in all different shapes and sizes, but the basic Toth acoustics and fundamentals of the setup and analysis are all the same, regardless of the complexity of the scanner or the number of Toth groups. The mechanics also have a great impact on the quality of the Toth data. Smooth, clean acquisitions make analysis more simple. Smaller hand devices, or where the encoder is basically connected directly to the probe holders and dependent on the human hand moving that. We can see two examples here of a best case mechanics and probably a worst case mechanics. It's very dependent on the operator to control that, where an automated scanner isn't used. And again, it affects the quality of the Toth inspection greatly. The mechanics, which includes coupling of the probes and stability of the probes as it's moving along the weld axis. In creating a Toth group, we're going to focus the probes based on the angle of the wedge and the PCS, or probe center separation, of the two probes. The focal point is controlled by both of these parameters. In majority of our single group inspections on materials less than approximately 50 millimeters, we're going to focus the probe beams to intersect at approximately 2/3 or 66% of the thickness. Here we see a typical Toth inspection where the PCS and angle has been manipulated to intersect at approximately 2/3 of the component thickness. This is a simple formula that includes the thickness of the component times 2 times the focal depth times the tangent of the angle to give us the PCS that we're going to lock the probes into the scanner. The PCS strategy is an essential variable, and again, it is essential for accurate depth and height sizing and the detection of the Toth group. This can be done with a calculator or more commonly in the beam plotters associated with phased array and Toth inspection. Both the ES beam tool and the Olympus setup builder contain beam plotters where a percent thickness or specific depth can be created to help the operator visualize the PCS and the proper angle, all of which are essential variables in the Toth inspection scan plan. The area of interest for a Toth inspection includes the understanding of the A-scan basics. Again, prior to the demonstration of the setup of a Toth group, we're just covering this in a very basic cursory way. In the download includes the complete training material for these topics in more detail. So our A-scan basics include setting the range so that the lateral wave, back wall, and in some cases, if desired, the shear wave signal is visible on the screen. In between the lateral wave here and the back wall here, the software can calibrate the UT axis or linearize the screen for precision depth and height measurements. After this back wall indication, we can see the shear wave mode converted signal that's generated in any L wave inspection, but it's not capable of being linearized. The benefit is for detection and length sizing, supplemental information from what is in between the lateral wave and back wall, and for that reason, it is often included in the digitized range when we set up the Toth group. The basic raw ingredients of the Toth group include the 6 parameters here. If 2 or more of these variables are known, the software can calibrate the rulers and cursors to convert time of flight in microseconds to distance in millimeters on the UT axis. The quality of the Toth calibration determines the sizing precision for depth and height. It is completely dependent on the operator of identifying these signals accurately for a precision inspection. Note that the beam angle is not a variable that's used in Toth. The only reason it exists in the software is to record the probe angle used during the inspection. The material velocity, and for carbon steel, this is going to be a constant, not a variable. The wedge delay that we're going to talk about in more detail during the calibration should be known to the operator prior to the inspection. This is the wedge delay of both the transmitter and the receiver combined together. The probe center separation is the distance between the exit point to exit point. And then the data itself, the time of flight of the lateral wave, the back wall, or any signal in between them is where we're going to identify with cursors for precision measurements. The Toth inspection records include the unrectified A-scan with sufficient range to include the lateral wave and back wall, and often the mode converted signal. In a clean weld with no defects, we will see the lateral wave connecting directly between probe transmitter exit point and probe receiver point and the back wall. Anything between these 2 signals is potentially an indication or a flaw. We'll see here an example of a flaw in the volume of the weld in between the lateral wave and back wall. The phase of this signal is important in our analysis for flaws that are either in phase or out of phase, breaking negative, positive, negative, or positive, negative, positive. The setup and configuration for acquiring Toth in an OmniScan SX, MX2, or any instrument really requires the part and weld definition that we'll do in the wizard, creation of the Toth group using the OmniScan setup wizard. We're going to configure the UT for all of the parameters to optimize it. Everything in the Toth inspection is about signal to noise ratio and reducing the noise as much as possible. The use of accessories, cabling, long cable, extension boxes, different types of probes either contributes to or reduces the noise in the signal. And as Toth is a very sensitive low-level inspection, those parameters are critical to the quality of the detection and sizing. We're going to configure the scanner and encoder. We will then prepare the OmniScan to do a live acquisition, and then we're going to save the data file for analysis offline. In this example, we see a very typical 2-phased array probe and single Toth inspection. That would be a 3-group inspection of which the Toth uses a single A scan. In the OmniScan, we're going to start with a basic Toth group by creating File, New. Under the File main menu and Setup submenu, select New. This is going to clear out all existing configuration from the OmniScan. If this is a Toth group on the end of a multi-group phased array inspection, of course, we skip this part. This starts with the Part and Weld wizard. The Part and Weld wizard under the wizard main menu is common parameters for all groups, Toth and phased array, in the inspection. It is an assignment of the thickness and a velocity for both shear wave and L wave that is typical of the Toth. In the Toth group, we're going to select a plate or girth weld mode, and no weld overlay is associated with the Toth inspection. This is a 1 or 2 part wizard, and we select finish to enter those parameters to make them common to all of the groups, phased array or Toth. We move after Part and Weld wizard to the Setup wizard. The Setup wizard walks the users through all of the parameters necessary to create the phased array, UT conventional, or Toth group. The first series of questions in the Setup wizard are first the operation. You have the ability to modify, add, or delete a group here. In this example, we're using the first group as our Toth group in a single group inspection, so we're going to modify group 1 that's already assigned as the UT Toth, and we will see 3 modes of operation for the groups. These mainly are from where does the group is generated and what type. For the Toth, the normal Toth group and most common is use of the UT connectors. Use of the UT connectors directly on the OmniScan module allow a higher voltage and an independent high definition UT board independent of the phased array to generate the Toth group. And that would be the conventional ultrasound using the UT LEMO connectors on the instrument that you see here. When a second or third group is required, or if the Toth is being generated from an accessory driven through the phased array connector here, we're going to select the UT conventional ultrasound using the PA connector. The main difference between these two is the voltage and the high definition independent UT board that we can generate the Toth group using the UT connectors here. The last option in the Toth wizard at this point of the setup is either a non-parallel or parallel Toth inspection. The parabolic cursors of the Toth analysis functions, the algorithm used to linearize the screen, and a few mechanical issues separate these two. The overwhelming majority and typical Toth inspection we see here is a non-parallel, and what the non-parallel refers to as the beam orientation is perpendicular to the weld scan axis as opposed to parallel. So our typical Toth inspection you see here would be a non-parallel inspection. The wizard continues on to the parameters of the probe. The main parameter needed to know is the frequency. The frequency will adjust the pulse width appropriately, and the refracted angle. The refracted angle only exists in the software for a report or recording of what angle was used for procedure compliance. The refracted angle plays no part in the algorithms or calculations for depth and height. It's only as a recorded part. The wizard also allows, under the edit button here, to enter the specific wedge and probe model from the database, but it's not necessary for the acoustic performance. Continuing on in the setup wizard, the next step is the offsets and the PCS. The scan offset we see here is only used when multiple Toth groups or phased array is combined with the Toth. This parameter needs to tell the software the distance between the beam center point of two or more groups of probes. When I hit the start button on the OmniScan inspection, it's going to make one of these probes 0 on the scan axis, and the trailing or leading edge probe is defined by entering that offset distance here. In this way, the multiple groups are seen at the same scan position in the analysis. The OmniScan has a function that defaults the PCS value automatically to 2/3 of the thickness based on the current setup. This can be modified or changed at any time needed. It's just a quick default to save the user having to do the calculation himself. After completion of the wizard, the Toth group is created, and we see a single A-scan visible on the OmniScan. We're going to configure the UT parameters next, which includes the general, pulsar, receiver, and advanced submenus of the UT setting main menu. You see coming directly out of the wizard, a default wedge delay was placed into the UT wedge delay. This would be the sum of both probes' wedge delay, the transmitter and the receiver. Using the most common Olympus wedges for 3 to 6 millimeter probes is the Olympus STI series of Toth wedges. This wedge delay for flat plate or girth weld parallel surface inspection will always be between approximately 5 and 6.5 microseconds. When using these probes and wedges on anything flat or girth welds for pipe to pipe, which is the majority of Toth inspections, any wedge delay should not be outside of that range, or it's an indication of a problem. We're also using a standard velocity from the database of 5890 that we'll talk a little bit more about as well. So our first function coming out of the wizard is to set the range appropriately so we see all three of our indications. The OmniScan has a negative square wave pulsar, all generations of modules, meaning the lateral wave connecting the two probes directly on the surface will always break negative first. If your signal is breaking positive, you probably have the wrong one. So open the range up wide enough to see all of the data and make sure you set your range appropriately. If you're doing the same inspections repeatedly, these numbers should start to be familiar to yourself. So in this case, we have the range start at 8 microseconds, and we have a 5 microsecond length to include the lateral wave, the back wall signal, and enough range to also include the shear wave mode converted signal that is visible with any angle beam L wave inspection. Coming out of the wizard, first thing we do is set the range appropriately to see our three relative signals. Moving to the pulsar of the UT submenu, we're going to set the voltage. Normally, Toth is a high voltage inspection. A big benefit of the OmniScan is an independent high definition, high voltage dedicated UT board. So we're going to use what works best but in most carbon steel inspections, we'll see that the high voltage is recommended. The frequency of the probe was set during the wizard setup operation, and it automatically configures the pulse width appropriately. 500 divided by the frequency will be our pulse width we need for both shear wave and L wave inspections. This can be fine-tuned here or just left with the default. The acquisition rate should be under optimum. The Toth group uses a single A scan and a very small data file, so we need not increase this much faster than we need for the scanner to minimize the noise. Use of accessories like remote pulsar receivers we see here in different forms connected to the scanner, typically in between the receiver and probe of the instrument, or in between both the transmitter and receiver in a remote amplifier pulsar receiver. These increase the signal amplitude of the relative lateral wave backwall and flaws without increasing the noise. We generally use these for long cables. The shorter the cables are, the less the need for these, using some of the older modules that didn't have as powerful as pulsar, or using phased array connector to generate Toth groups at a lower voltage. We can improve the SNR, or the signal to noise ratio of flaw data, by use of these accessories. Generally, with 2 meter or 3 meter, 5 meter cables, this is not necessary. Moving to the UT receiver, the filter, under best case conditions, it's recommended that no filter is used. Some of the codes and work procedures specifically prohibit use of smoothing and filter of the raw waveform data. Averaging is selected based on what works best. The averaging factor will create an additional A scan for each factor of 8 in this example, and it will sum all of them together, subtract the difference, and reduce the noise that we see as compared to the relative signals. This averaging, historically for Toth, is most useful for use of long cables and accessories and extension boxes. The shorter the cables are, the less averaging you're going to see. In most 2 or 3 meter cable inspections, we might not see any benefit at all to averaging. So use what works best based on the SNR of the signal as you experiment with this. It has a very low effect on the overall PRF because these are individual A scans. Set the inspection type and configure the scan axis for encoder 1. Okay, we have completed the UT optimization after the setup wizard. Now we're going to change the default inspection on the OmniScan from time to encoder 1. For most of Olympus's standard encoders, it's going to be an encoder 1 pin out on the scan axis. The overwhelming majority of Toth inspections are not using a 2-axis or raster scan, so we'll select encoder 1 here to prepare the inspection for recording the data. Under the same scan menu, the encoder parameters, typically most most encoders commercially available and all of the ones from Olympus are quadrature type encoders. This is a hardware function. The encoder resolution can either be calculated by a wizard under the calibration menu or entered directly here. The normal operation would be to drive the encoder a fixed distance using the manufacturer's encoder resolution and validate that it has driven a specific distance within a certain tolerance. If every inspector is using the same encoder with a different resolution, it's going to hurt repeatability. Again, these encoders are, all the commercially available ones are dependent on the user getting a good grip and adjusting it correctly, but that number should not change over time unless there is really a problem with the encoder, the wheel is worn, or the rubber around the wheel has become distorted. We're going to configure the area of our inspection. This is the length of the scan axis, the start position and end position. This also allows us to program a series of Toth inspections, 0 to 1,000 millimeters, 1,000 to 2,000 millimeters, so on and so forth. The scan resolution is the distance between any two data points. That would typically be 1 millimeter or 40 thousandths of an inch for typical inspections. This affects the size of the file and the speed of the scanner much more in phased array than in Toth, because again, we're only using a single A scan or even in a multi-group Toth inspection of 2 or 3 A scans. At this point, we've completed the group setup. We have completed the UT optimization, and we have added a scanner or encoder to the inspection. Prior to doing the inspection on an actual plate or pipe, we're going to calibrate the A-scan for wedge delay and PCS. This is a step many OmniScan owners skip. It's not recommended to do that. The benefits I'll explain in analysis mode, but prior to setting the scanner on the pipe, if we set the scanner on a flat block or pipe of known thickness, and by known thickness I mean not a nominal thickness, but something that was measured with mechanical calibrators, calipers, or a reference standard like an IIW block of known thickness. The reason we're going to calibrate the wedge delay and PCS on a reference standard prior to the inspection on the pipe is so that we know the real wedge delay and the real PCS value. And this will be explained in a little more detail in analysis as well. Any of the two options here that require two functions, wedge delay and PCS, or velocity and wedge delay, require two targets, typically the back wall and lateral wave. The single wedge delay option only requires one target and makes an assumption that PCS and velocity are constants in the inspection and not variables. So again, we're going to, on the calibration standard or plate or pipe of mechanically measured known thickness, we're going to enter the wizard menu, calibration submenu, and we're going to select mode, PCS, and wedge delay, start. It's going to walk us through a wizard where the thickness is coming in from the original setup and our PCS value that was calculated or entered by the operator. At this point, the PCS is theoretical. It was calculated by a calculator, and the operator attempted to space the probes as close as possible to this number and lock them in place. No matter how hard you try, the only way to lock the probes in the scanner is visually using a ruler and lines on the wedges, but historically, I would say operators can get within maybe 3 or 4 millimeters of this actual distance. So this function is going to change a theoretical or mathematical PCS to the real PCS so it is known to the software. The wizard steps us through to the end where we are going to place a cursor on two targets. Again, when we're calibrating for two functions, the software is going to ask us for two targets. The first target is the lateral wave here. Okay, red box, red cursor, the position at 0 millimeters, which connects the two probes on the surface of the lateral wave, is at 8.55 microseconds. There is a measurement taken at the peak of the negative wave. Also, in some cases, that measurement might be taken here, directly between the negative and positive. It's important to be consistent and use your training and work practice. The overwhelming majority of the measurements are taken directly from the first negative peak. And again, the OmniScans always break negative first because they have a negative square wave pulsar. Okay, the second target it's asking us, green box, green measurement cursor, is the back wall, typically. This could be any two targets of known depth, including side drilled holes, but typically in a single zone Toth, it's going to be based on the back wall. So at 9.67 microseconds is the full thickness of the component at 12.7 millimeters. We're looking at a 1/2 inch calibration plate or calibration pipe of known thickness. The operator selects Calibrate Wedge Delay and PCS. And the software calculates the new wedge delay and the actual PCS. So we used a default velocity in carbon steel of the database, 5890. That was a constant in this calculation, not a variable. The calculated wedge delay was very close to the initial estimate at 6.21. Again, if I'm using the same wedges and probes every day, that wedge delay should not change other than when the wedge is worn slightly. All of the STI wedges from Olympus will have a wedge delay of about 5 to 6.5. If this number comes up other than that, you probably selected the wrong target or used a depth other than the depth of the actual component. And now we see a new PCS. The operator attempted to set the PCS as close as possible to his desired focal point, but with a known calibration standard, the software knows the real PCS. And as long as it's within a couple millimeters of where you want it to be, it's more important that the software knows the real value. That PCS now is a constant for future calculations. It's not a variable. Once we take the scanner off the pipe of the calibration standard and move it to the pipe on the inspection, we don't know what the real thickness is. So that PCS is going to be a constant. And we'll talk a little bit about under what conditions that doesn't become a constant when we get to analysis mode. Okay, we're going to accept this value from the calculation here. And in addition to now knowing the real wedge delay and the real PCS of the scanner with the probes locked, the screen is linearized. There's an algorithm that in between our two targets, the lateral wave and back wall, we will see the lateral wave at 0 millimeters and the depth of the back wall at the correct thickness, whatever you entered it in. We will see the microseconds reading and the millimeters reading in between the lateral wave and back wall. And again, I had a few questions in the Q&A. Again, the PCS is the probe center separation. It is the distance on the surface from the transmitter exit point probe to the receiver exit point probe. And in the download material, there's lots of pictures and much more information about this, so it will be clear. After we have done the calibration, we can also right-click on the angle in the OmniScan interactive header and see our calculated PCS and the information of the probe and wedge from the wizard. Okay, this thickness, this PCS will become constants in the future inspections so that we don't have to use two targets in analysis mode. And I'll explain this more when we get to analysis. Okay, at this point, the OmniScan is ready for the inspection. We're going to save the file, press and hold over this area of the OmniScan, and name the setup OPS file something logical. Anytime you see a little star next to the OPS name here, it's an indication that something has changed prior to saving the file. So save the file at this point prior to the inspections. Okay, at this point, I have picked the scanner up off of the calibration block, and I am on an actual pipe or plate for a real inspection. I know the real wedge delay, and I know the real PCS as long as the basic surface conditions are flat and haven't changed. We're going to put the OmniScan in full screen mode, and from the interactive title bar here, we can change the polarity or the distance direction of the scanner. The area that we defined under the scan area menu in this example was 0 to 200 millimeters. Anytime the encoder position is outside that defined area, we will see a red indication here. As soon as the encoder is reset to 0 or the scanner is brought within range, we will see this red background change back to blue, and the OmniScan is in a position to acquire data. We're going to move the scanner, acquire the data file, and select pause and save the data file. The position of the lateral wave on the actual inspection is very significant. Okay, if I'm looking at operators preparing to do an inspection, one of the first things I do is ask them, what was the position of the lateral wave on the calibration block? At what point in time did the lateral wave arrive? If the arrival is within a half a microsecond or maybe a little more than that as the calibration block, in other words, if this signal's arrival time at 7.5 microseconds is the same or very close as the calibration block, it's telling me that the surfaces are flat. The pipe is not mismatched for the fit up. It doesn't have any distortion. It's basically the same condition as my calibration block. When that is true, I know that my PCS value is still valid and my wedge delay is still valid as well. Notice I acquired the data in an uncalibrated state. The pink ruler that we see here is in microseconds. It was uncalibrated. The calibration was removed for the actual inspection, but my PCS value, the probe center separation value, the physical distance of the probes in the scanner, and the wedge delay was known and entered into the software. I only acquired the data at an uncalibrated state with a time scale only. This is intentional for reasons I'll explain shortly in analysis mode. Again, the position of this lateral wave on the actual inspection surface being the same as the position of the lateral wave on the flat calibration block or pipe of known thickness tells me that the PCS and wedge delay are valid for the inspection. And that's a very important point, as they're not always that case. The overwhelming majority of new Toth users don't go to that extent to define the PCS and wedge delay initially, and it hurts them in their depth and height sizing after the inspection. It does not hurt them in detection and length sizing generally. So again, before we go to analysis mode, I want to review again what our essential variables are. The material velocity of carbon steel, we used a default database value. There's no reason or benefit to calibrate it using the Toth. If you don't know the velocity of the material or have reason to think it's different from some unusual type, it needs to be calculated ahead of time. The worst case scenario is all inspectors using a different velocity, and we'll talk about that in a minute as well. The wedge delay was calculated first from the database when a default value was placed there by Olympus software. It was determined using the wedge delay PCS calibration option of our calibration wizard and our probe center separation. Again, there were a few questions about this. This is the distance between exit point of the transmitter here and exit point of the receiver here. The closest you can get with the naked eye and mechanical fingers trying to tighten that up is within a few millimeters. It needs to be a precise measurement calculated from the wizard for precision inspections in the future. And then the time of flight of the lateral wave, back wall, or any indication is completely dependent on the operator identifying these. So we're going to move to analysis of this same data file here. What analysis consists of a Toth screw is first, we're going to straighten the lateral wave. The lateral wave, as the scanner is moving, is normally jagged, rigid, and can deviate by a fraction of a microsecond. As long as there's no flaws breaking the surface, that can be straightened. Okay, then we're going to do a single target wedge delay calibration. If we did a wedge delay in PCS on our calibration block, and if the lateral wave position arrives at approximately the same time, it is only necessary to do a single point wedge delay calibration to linearize the screen. And we'll demonstrate this. We're going to do the analysis of Toth defects, including placement of cursors, and we're going to record the defect. So I'm going to switch now to live Omni PC here, and we're looking at the same data file we just discussed acquiring. I can see that the data file was acquired without a calibrated linearized screen because the time scale here. My lateral wave arrived at 7.8 microseconds. This is close enough to the calibration block lateral wave that I can determine that my PCS is still valid, meaning the PCS is going to be a constant in calculations, not a variable. And I can see that the data quality is a high SNR. My lateral wave is coming in at approximately 50%, 60% amplitude. And I have a good back wall and a good, a good back wall and a good shear wave mode converted signal. I'm going to take a quick look at the UT menu. Okay, the operator used a database velocity. If I see a same series of files from the same pipe that were all acquired with a different velocity, it is a red flag. It is a problem with the work procedure. If the probes are locked into the scanner and you're doing the same series of inspections, there's no reason that the data files would include a different velocity. I see that the wedge delay was within what I normally know it to be. This is something we're going to change in analysis mode as well, but it was acquired with a wedge velocity very close to what I know is normal. Right-click on the interactive header for the setup configuration. I can see that the PCS value here was calculated as well. That value, because the lateral wave arrived at a similar time of flight as the cow block, I am not going to change this. If I don't know the real thickness of the pipe, I can't recalculate the PCS with a nominal thickness. Use of a nominal pipe thickness of an unknown pipe has no value in increasing the precision of the inspection. So my first function is to straighten this lateral wave. We can see as the scanner's a little jittery, there's a little bit of difference in the microsecond arrival time. Prior to doing a synchronization function, I'm going to make sure there are no surface breaking defects. If I have surface breaking defects, the lateral wave synchronization function will hide and obstruct them. So this function is available from a right click or press and hold on the touch screen directly on the B scan, lateral wave synchronization. Okay, the lateral wave is straightened so that the arrival time is within a fraction of a microsecond for all A scans. This removes the jittery part of the scanner as it weld wanders or moves slightly side to side, changing the time of flight. When the lateral wave is straightened and I know that it has arriving at the same time as the calibration block, now I need only do a wedge delay calibration. The shortcut for the top calibration on the B scan will always display the last function used. We don't want to do wedge delay and PCS on the inspection data because we don't know the real thickness. It could vary 10% or it could be corroded or anything. So we're going to enter the OmniScan wizard, calibration. We're going to set a reference A scan that has a good lateral wave position, and in this case, we'll use the center of the flaw. We will select wedge delay only. In the wedge delay, we only require a single target, which is normally going to be the lateral wave, or a side drilled hole of known thickness if we can't see the lateral wave or back wall in a multi-group. I have everything I need to calibrate current here, but we'll step one more distance here just to see the wizard step. The software is assuming that the PCS is known and valid. So I need only set the position of the lateral wave to redefine the wedge delay at 0 millimeters or 0 inches on the component. Select Calibrate. Now we see the microseconds and the millimeters on the linearized portion of the screen. Here we see at 12.7 millimeters the back wall indication, and at 0 millimeters we see the surface. By default, the cursor positions do not have the values displayed. To visualize the values, we go to, and we'll accept this value, we'll go to Display, Overlay, Cursors, Values. So turn these values on so we can see them. The flaw, we will zoom in over our area of interest. We will set a reference cursor here that has now been linearized. We will use our parabolic cursors to define each side of the flaw. And again, this webinar doesn't get into cursor placement too much. In the download material, we'll see more examples about this, but the hyperbolic cursors on a non-parallel scan are designed to assist in our length sizing. So when we selected the Toth in the setup wizard, it also defined the Toth reading lists for the 4 groups of 2 for the relative readings. The Toth indication you see here is an ID-connected crack breaking the back wall. It is at a depth of 7.92 millimeters here for a total through wall height of 4.78 millimeters between the back wall or inside surface and top of the flaw. And it has a length of 13.75 millimeters. So we typically oversize flaws in Toth and phased arrays, so be very conservative. Use the parabolic cursors to identify the flaw. We can display our indication table here, and under measurement indication tables, we can add the readings that define the cursor position and the flaw. It will include in the report an image of the B scan and A scan or whatever is displayed at the time the indication is added, and completes analysis. For the recording of defects. I want to thank you for joining us. If you are an OmniScan SX, MX2, or an Olympus Focus owner and would like a private webinar to elaborate on any of this information that has been presented or to discuss your own needs, respond to the email in the download and we will contact you. This is something that's very easy for the help desk at Olympus to do. Most things and questions and problems can be straightened out in a 30-minute or 1-hour session, and we are making that available to any of the participants of this webinar or any of the OmniScan owners as well. So there will be a download with the complete Olympus OmniScan Toft training program and some sample data files, including the ones that were presented in this webinar. I want to thank everybody for attending, and we will see you at the next webinar. Thanks again. I'm going to turn it back over to Greg now, and you can expect an email blast shortly with the download material I mentioned. Thanks again.
Thanks, Chris. On behalf of Olympus, I'd like to thank all of the attendees for joining us today, and Chris for his expertise and participation in today's event. We hope the material presented was informative and useful. This webinar, along with the Q&A session, will be archived on our website at www.olympus-ims.com. Everyone who registered for the event will receive a follow-up email regardless if you joined us or if you didn't. And that email will have links to the archived presentation and the document downloads that Chris alluded to and the materials that you saw here in the presentation today. That's going to do it for today. Thanks again for attending, and we'll see you again next time.